For the experiment, we choose affordable and uncooked spaghetti as our model to construct a solid bar measuring 30 cm long and 1.5 cm thick. Specifically, our project tests a square cross-section shape to evaluate its structural strength under high pressure. We conduct the structural test by hanging a water bottle and gradually increasing the load until the square bar reaches its ultimate breaking point. To guide our study, we established 5 key objectives. First, to construct the square-shaped spaghetti bar to the exact requirement dimensions. To observe and analyze its bending behavior and structural response under stress. And then to identify the maximum failure load and calculate the ultimate normal stress at the exact moment of breaking. Next, to plot accurate shear force and bending moment diagrams derived from our final test result. And the last one, to establish a safe allowable normal stress limit by applying a standard safety factor of 1.5.
This process aims to fabricate a spaghetti beam for a bending test. The beam is made using uncooked spaghetti with length of 30 cm and a square cross-section measuring 1.5 cm by 1.5 cm. During the testing phase, the beam is loaded by hanging a water bottle and the load is increased gradually until the beam fails. The materials and apparatus used in this project are a rope, a hanger, glue, uncooked spaghetti, roller, and a water bottle. The roller is used to measure the beam dimension. The glue bonds the spaghetti strands together, while the rope, hanger, and a water bottle are used during the bending test. The fabrication process begins by arranging 8 strands of uncooked spaghetti parallel to each other. Next, the strands are bonded together using glue. These 2 steps are repeated until 8 bonded layers are obtained. Then all 8 layers are glued together to form a square cross-section. Finally, the complete spaghetti beam is left to dry and is ready for the bending test. This slide shows the final dimension of the fabricated spaghetti beams. The beam has a length of 30 cm and a cross-section with a thickness of 1.5 cm. These dimensions follow the project specification to ensure a fair and consistent bending test.
Now, I will explain the testing procedure of our spaghetti beam. First, the spaghetti beam was placed on 2 supports for the bending test. Second, empty water bottle was then hung at the center of the beam where the load will be applied. Next, water was added gradually into the bottle in increment of 1000 ml. At each loading stage, the volume of water was recorded and the condition of the beam was carefully observed. Finally, the loading process was continued until the spaghetti beam fractured. The data collected from each loading stage then were used for the calculation and also to generate the shear force and bending moment diagram. Now, let's watch the testing process.
Now we calculate the shear force and bending moment for 1 liter. So first we use the summation of vertical forces to find AY, and we use the summation at moment A to find BY, which both are 4.905 newtons. Next we cut the diagram into 3 segments. The first segment we use the summation of vertical forces A0 equals to AY minus V1, and we get V1 is 4.905 newtons, and then the sum of moment we get M1 is 0.7358 newton meter. For the second segment we do the same. We find the sum of vertical forces, is equal to 0, so 0 equals to AY minus 9.81 minus V2. We get V2 is negative 4.905 newtons, and moment for M2 is 0.7358 newton meter. And for the third segment, we find the same thing. We find the vertical forces AY minus 9.81 minus V3, and we get V3 is negative 4.905 newtons, and the sum at the sum for moment at segment 3 is 0 newton per meter. Now we generate the shear force and bending moment diagram. For our shear force diagram, the shear force increases to 4.905 up until 15 centimeters and changes to negative 4.905 and ends at 0 at 30 centimeters. And for our bending moment diagram, it increases until 0.7358 and then at 15 centimeters, and then it decreases to 0 at 30 centimeters, reaching a peak of 0.7358. Now with the calculation at 2 liters, so just like before, we use the summation at moment of A to determine By force, which is 9.81, and summation of vertical forces to find AY, which is also 9.81 newton. Like before, we cut it into 3 segments. At segment 1, we find vertical forces is equal to 0, so 0 equals to AY minus V1, and V1 is 9.81 newtons. The sum of moments, we get M1 is 1.475. For the second segment, Fy is equal to 0 again. 0 is Ay minus 19.62 minus V2. V2 is negative 9.81 newtons. And the sum moment is 0, and we get M2 is 1.4715 newton meter. At the third segment, Fy is equal to 0, Ay minus 19.62 minus V3, same, negative 9.81 newton for V3, and the sum at moment is 0, and we get M3 is 0 newtons per meter. So the shear force and bending moment diagram for 2 liters. For the shear force diagram, it increases to 9.81 up until 15 centimeters, and it drops to negative 9.81 up until 30 centimeters, where it drops back to 0. And for our bending moment diagram, it increases proportionally to 1.4715 at 15 centimeters, and then drops back down to 0 at 30 centimeters, reaching a peak of 1.4715 newton meter. Next is at 3 liters of force. So like again, we calculate By using the moment at A, which we get is 14.715 newton meter, and the vertical forces, we get Ay, which is 14.715 newtons. So the first segment, for vertical forces is equal to 0, so 0 minus Ay minus V1 is equal to 14.715 newton, and the sum of moments we get is equal to 0, so M1 is 2.2073 newton meter. Second segment, Fy is equal to 0, so 0 equals to Ay minus 29.43 minus V2, and V2 is negative 14.715 newtons, and the sum of moment is equal to 0, M2 is equal to 2.2073 newton meter, equal to M1. And the last segment, Fy is equal to 0, and we get V3 is negative 14.715 newtons, and the sum segment 3, M3 is equal to 0. Now is the shear force and bending moment diagram for the 3 liters. For our shear force diagram, we start at 14.775 newtons up until 15 centimeters, and it drops to negative 14.75 all the way until 30 centimeters, where it drops back down to 0. And for our bending moment diagram, it increases proportionally to 2.2073 until 15 centimeters and drops back down to 0, and reaching a peak of 2.2073 newton meters.
Okay, for calculation at 4 liter, we need to calculate the support reaction force before we calculate the shear force and moment. For the support reaction, we make summation moment at A equal to 0, and we get By 19.62 Newton, while Ay we need to summation Fy equal to 0, and we get Ay equal to 19.62 Newton. For the shear force and moment, we calculate by section. So the first one, V1 and M1, we get 19.62 Newton, and M1 we get 2.943 Newton meter. For the second section, V2 we get negative 19.62 Newton, while M2 we get 2.943 Newton meter. And the last one, we get V3 and M3, which is for V3 we get negative 19.62 Newton, and for M3 we get 0 Newton meter. After we calculate the shear force and bending moment, we need to generate the shear force and bending moment diagram. Okay, for the shear force diagram, at x equal to 0 to 0.15 meter, we get 19.62 Newton, and from 0.15 meter to 3 meter, 0.3 meter, we get negative 19.62 Newton. Okay, for the bending moment, the bending moment maximum, we get 2.943 Newton meter. Okay, so for the last one calculation, which is at 5 liter, we need to calculate the support reaction first. Okay, for summation MA equal to 0, we can get dy equal to 24.525 Newton, while summation Fy equal to 0, we get Ay equal to 24.525 Newton. Okay, so for the shear force and bending moment, we can calculate by section. Okay, for the section 1, summation Fy equal to 0, so we can get V1 equal to 24.525 Newton, while when we do summation M equal to 0, we can get M1 equal to 3.679 Newton meter. For the second section, summation Fy equal to 0, we get V2 equal to negative 24.525 Newton, while summation M equal to 0, we get M2 equal to 3.679 Newton meter. For the last section, when we calculate at summation Fy equal to 0, we get V3 equal to negative 24.525 Newton, while summation M equal to 0, we get 0 Newton meter. After we calculate the shear force and bending moment, we need to generate the shear force and bending moment diagram. Okay, for the shear force diagram, from 0 to 0.15 meter, we get 24.525 Newton, and from 0.5 meter to 0.3 meter, we get negative 24.525 Newton. Okay, for the bending moment diagram, we get bending moment maximum at 3.679 Newton meter.
This slide shows the calculation of the allowable normal stress. The failure load is 5 liters, which is 49.09 newtons, and the maximum bending moment is 3.679 Newton meters. Using the bending stress formula, the failure normal stress is 6.54 megapascal. After applying a safety factor of 1.5, the allowable normal stress is 4.36 megapascal.
Moving on to our conclusion, regarding model fabrication, we successfully created the 1.5 cm by 1.5 cm square composite beam by gluing multiple strands of uncooked spaghetti together in parallel layer. During the bending test, the beam displayed a very predictable elastic behavior before failing. Its ultimate load capacity reached an impressive 5,000 milli of water in terms of structural efficiency. Because the beam itself is impressively lightweight but supports such a heavy load, it achieved an incredible strength-to-weight ratio of 1,000. This strongly proved that core layer fabrication method successfully optimized the natural strength of the materials. By applying our target safety factor of 1.5, we can safely calculate the allowable stress limit to guarantee the design remains within a safe structural boundaries. In conclusion, this experiment successfully proved that theoretical concept of bending and internal stress perfectly match physics real-world testing result. The data clearly demonstrate that both the cross-section shape and the precise fabrication method have a massive impact on a beam's ability to support heavy loads. Thank you.